Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. In this, the final episode of our AI in Sports series, I'm joined by Stephanie Kovalchik, Research Fellow at Victoria University and Senior Sports Scientist at Tennis Australia. Stephanie and I had a great conversation about a few of the many interesting projects underway at Tennis Australia. We start out taking a look at their use of data to develop a player rating system based on ability and probability, as opposed to the current official one, which is based on points scored and match results. We then get into some of the interesting products her Game Insight group is developing, including a win forecasting algorithm and a statistic that measures a given player's workload during a match. Stephanie details her paper, Is There a Pythagorean Theorem for Winning in Tennis?, which explores the development and application of a Pythagorean theorem for win expectation in tennis. We also take a look at her project to develop a system for classifying ending shots and an emotion tracking system that helps show the link between emotion and performance in tennis. All right, on to the show. All right, everyone, I am on the line with Stephanie Kovalchik. Stephanie is a research fellow at Victoria University and senior sports scientist at Tennis Australia. Stephanie, welcome to This Week in Machine Learning and AI.
Hi, Sam. Thanks for having me.
Absolutely. Why don't we get started by talking a little bit about your background? You've got a background in statistics, but you're applying that to the field of tennis now. How did that come about?
Yeah, it's kind of an interesting one. I guess to go way back, I was always really interested in science. And so I knew definitely that I wanted a career in science, but I actually started out kind of more interested in neuroscience. When I was an undergrad, I was looking into biology and really thought the brain and how it worked was fascinating. So I kind of thought I was going to do that. I was at Caltech, and then I spent a year after graduating just doing pure research. And I was collecting data and starting to analyze it. And it was at that point that I realized how important stats were to science and reaching conclusions. And I really just wanted to do that all of the time. So then I looked to see, what programs I might go into. And I found a great one at UCLA. So I went over there and finished my master's and PhD there. And I was actually in biostat, so it was very applied, a lot of focus on applications of statistics to health and things like clinical trial design and studying diseases. And after that, I went to the National Cancer Institute, actually did a fellowship there, and it was all focused on risk prediction. But that was kind of my first place where I got a taste of real model building, and with an important practical outcome where our whole goal was to try to help doctors and patients better assess their risk for different types of cancer, and learned a lot just about the different approaches, particularly more from kind of the epidemiological point of view. So far you're probably wondering, where's the sports angle in all of this? I was on a very kind of, health statistician track. And on the side, it's a classic story in sports statistics where it's the hobbyist goes home and spends all of their evenings just scraping data and calculating percentages, and that's literally what happened. I mean, more after grad school, once I kind of had enough of a foundation, and I was always watching tennis. I just loved the sport my whole life, and I was starting to watch it from that perspective.
Okay.
And at that point, the whole Moneyball era in sport was well underway, but it never had really reached tennis. And I was just confused why weren't we seeing that same kind of advance? And I started looking on the web to see what kind of data was available in the sport. And there was actually quite a lot. at least when you're thinking of the kinds of data you might want for like building a rating system for players, for example, you could do that for all of the open era history in tennis just from publicly available data. So I started to take on like kind of small projects, but it grew over time. And then I was starting to present at sports conferences. And eventually that was how I learned about the role at Tennis Australia, meeting another sports scientist that was working there. And that was the first time that I realized that somebody could work full time on sports doing statistics. I figured you had to be doing it in baseball or basketball. I just wasn't even really pursuing that as a career. I just thought it would always be this passion, the side passion. Yeah. So luckily it turned out that I just didn't realize the opportunities and kind of stumbled on one. And I've been in that role for 2.5 years now. And it's really a dream situation.
That's fantastic. Did you play competitively growing up or in college or something like that?
In high school. I mean, that was about the extent of my ability. But it was one of those things where, like, first sport that I really learned with my dad, and so it kind of had a special place. And there's something appealing just about the individual nature of it. You're out there and you're totally alone. I mean, there's nobody that's going to help you with any of the decision making. And so I think that really lends itself to kind of, an interesting drama and stories that make, the whole journey of individual players that much more interesting.
You mentioned using open data to come up with a rating system. Now, as I understand it, tennis has a well-established formal rating system. What would be the relationship between that type of the formal system and one that you'd come up with openly available data?
Yeah, so tennis does have official rankings, and those are based on a point-based method where players basically rack up points based on their performance at individual tournaments. And the bigger the tournament, the more points they get, and the deeper that they go in that event, the more points that they get. But it's not actually tied in any statistical way to the expectations about what they should be doing and how difficult their opponent is. So one thing that statisticians working in tennis have been interested in is whether if you have an approach that is based sort of on the probabilities around individual match results, if that would give you a better assessment of a player's overall ability, because it's directly tied to what they're expected to do and how they're actually performing. So as an example, an alternative to the official rankings would be an ELO-based system, and that would be an example of one that's a probability-based way of measuring player ability. It can also be applied to teams, and in fact is used by a number of professional teams. It was actually developed originally for chess, for rating chess players, but that's a system that's really well established. And my group, we have shown that it does outperform the official rankings just in terms of the assessment of player performance. So if you use it to evaluate how a player is likely to perform in the future, so use it as a basis for forecasting their future results, it does a better job than models based off of official rankings. So so that's one reason to prefer it. And you can also do fun stuff like look at surface-specific versions. You can try to focus more on a player's serve versus return, which is kind of a offensive-defensive type of breakdown. So it's something there's, I think, more research questions around even improving the current systems that are used. But all of those possible improvements can be done with open data.
So, Stephanie, you work as a data scientist as part of the Game Insight group at Tennis Australia. What exactly does that group do, and what's your day-to-day role as a data scientist there?
Yeah, GIG, as we call it, is sort of an academic industry partnership. So that's my two hats, doing research at Victoria University and then being part of this research group with Tennis Australia. So Tennis Australia and Victoria came together. They realized that there was this real opportunity in tennis to advance what's being done with data that's available. And so the Game Insight Group is really an initiative to try to take advantage of that opportunity. So it's a research and development group that's we include a number of data scientists, and we spend all of our time just focusing on questions of interest in how can we understand, why some athletes in tennis do better than others. I mean, ultimately, we're trying to kind of crack that question. And so we have a number of areas of research, and then we get the chance to actually create products out of those as well. So there's kind of a large translational component to what we do, where we're trying to not only address questions that are of interest to us, sort of as, academics and researchers, but that we think the results of pursuing that research could directly impact the sport and have benefit back to how athletes are training, how coaches are making decisions about their development. So that's one of the really exciting things about the role, is that translational piece. And so we are spending a lot of our time doing what you might typically think of with a researcher at a university, but then we also get the chance to participate with events, try to bring stats to life in actual matches for fans, and then work with players and coaches to help them as they're trying to pursue their performance objectives.
What's an example of one of the products that you've been able to create in the role?
So we have a number of stats actually that we debuted this year at the Australian Open. That's kind of our marquee event, as you might imagine, being at Melbourne Park. And so that included a win forecasting approach, which allowed us to let fans know what each player's chances were of winning the match at any point in time, and to contrast that with where they were at the start. So it kind of gives you an interesting idea about the momentum over the course of a match. We also had a work stat that we introduced, which I was really excited about, because tennis is a very physical game. There's so much interest in how players, how much effort they're making during matches, and how that's affecting their performance. But we don't actually have a lot of stats around the physicality of actual match play. So we have worked on a work stat that basically gives you a comprehensive look at how much physical effort players are making, primarily in their lower body. So by running around, changes of direction, accelerations, decelerations. We take all of that into account to come up with this overall work measure. And so that's another thing that's fun to look at, how different the two players in any particular matchup are as a match progresses. So every year, we are looking for new metrics that will give kind of a new perspective to the sport. And those were some examples that we introduced this year.
Oh, that sounds really interesting. Can you talk a little bit more about that work set? Where does the data, for example, come from?
So that's one that's based off of tracking data, which has kind of been a new thing. If you look across sports more broadly, tracking data is kind of the holy grail for a sports statistician, because it represents some of the highest quality information that's out there about performance. In tennis, it became more available with the introduction of the player challenge system, which is a multi-camera system that sits on courts and tracks the ball throughout a match. And it allows players to be able to review line calls if they think there's been an error made. They get to use a challenge, and then there's sort of a video graphic representation of where that particular shot landed with respect to the lines. For that to happen, there's all this data being generated about the position of the ball in space at any point in time. And it also has information about the player locations as well. So GIG, we have access to that tracking data for the Australian Open series events. So for that part of the calendar, we get a comprehensive look at the physical characteristics of shots and player movement. And so that would represent all hard court matches. And we have that going back to like 2012. So that's been a big area of development for us, is like what insights can we get out of those data that we can use in our player services or in enhancing the experience at events.
And thinking about that data source, multiple cameras, different angles, it strikes me that there are a ton of interesting machine learning and AI types of challenges in there to go from that to, some kind of representation of a player position or even player foot positions that will allow you to get to things like acceleration and distance covered and all these things. Is that processing of the video to get to some of the positional information? Are you involved in that, or is that done upstream to you and you get more refined information?
We're not actually collecting those data or producing those data ourselves. That's done by the company that's responsible for providing that challenge, the player challenge system, which is Hawkeye, who's now part of Sony. And they actually are that data provider for other sports as well. Like they provide a video review system for cricket, for example. So they're the data provider. And what we end up getting from those are summaries of it's effectively arcs of the movement of the ball. So a typical shot will have two arcs, and those are described with polynomial functions in 3D space. So you get a summary function, but it's at a very fine level of detail. And from that, you can derive a number of interesting things like the ball speed at any point in time, its height, its angular characteristics. So that's the data that we're provided. So it's not exactly raw in the sense that you're not looking at like coordinates in space. It's in a summary form, but it's still quite granular.
Okay. You mentioned earlier player acceleration, and I'm trying to envision how you might derive that from ball positions. Can you elaborate on that?
Yeah. So for the players, we actually have a 2D coordinate of the position of their stance. So it's effectively like the midpoint of their stance at any point in time.
Okay.
And that is tracked at like 25 hertz. So you get 25 samples per second of their XY position.
Okay.
And so it's from that we would derive anything around the player movement.
Got it. Super interesting. I did have a question from from looking at some of your publications on your website. One of your recent articles is there a Pythagorean theorem for winning in tennis? And in looking into that a little bit, like I didn't realize that Pythagorean theorems in sports was a thing, but it sounds like it's a whole thing. Can you talk a little bit about the background and implications of all that?
Yeah, it's actually a fun one, kind of historically in sports stats, because it was one of the things that Bill James, who's kind of now become like this, godfather of sports statistics. One of the things that one of his major contributions to baseball statistics was the development of this Pythagorean theorem, or sometimes you'll see it called the Pythagorean expectation. So sports statisticians spend a lot of their time thinking about how can they forecast outcomes in the sport, because if you can do that, it usually means it gives you a better understanding of why some succeed and others don't. And that's ultimately, a central question to a lot of what we do. So the Pythagorean theorem is one approach to looking at.
I'm getting the scratchy thing again.
Okay.
Sorry.
That's okay. I'm sorry. I was trying to manage my dog down there, and I think the mic moved around. Should I start back.
Sure, sure.
So the Pythagorean theorem, it's an interesting one historically because it was one of the major contributions of Bill James, who's become the sort of godfather of sports statistics. And what he looked at was a question around, how could you try to determine if a team, let's say, is midway in their season, what their likely overall win percentage is going to be at the end of the season. And so looking at that problem, he developed this Pythagorean expectation. And what I was interested in is whether a similar idea and a similar relationship existed in tennis. So the main thought behind it is that, how do you get a win? And in most sports, it usually means earning more points in some sense than your opponent. So in baseball, it's runs. It's all about, being ahead of your opponent in runs. The Pythagorean expectation shows that actually, if you look at the runs earned by a team over the course of a season against the runs that their opponents have earned against them, and you take the square of those, that ratio between the team's runs earned squared against the sum of that quantity and their opponent's runs earned is actually quite accurate of setting expectations for what a team's overall win record is going to look like in the long term. So that's where the Pythagorean label comes from, because if you look at these squared terms, it looks a little bit like the relationship between the sides of a triangle. So James was working at that like in the 80s, which, that's like ancient times from sports stats perspective. And since then, a lot of other statisticians have looked to see if similar relationships exist in their sport, because, most of us are all in that situation of like, you're just trying to earn more points. So maybe there's kind of a similar thing that you can find. And there have been applications of it in basketball, hockey, and it holds up, although the exponent, the sort of optimal exponent for setting those expectations varies from one sport to the next. And it's kind of interesting because if you look at that exponent, depending on what value it takes, it kind of tells you how important one additional point, whatever that point represents for that particular sport, it tells you how important that is in that particular sport. So if you're in a very high scoring type of sport like basketball, one additional point will generally mean less than an additional run in baseball, for example. So back to tennis. In tennis, it's kind of interesting because it's a hierarchical type of game, right? You have points within games and games within sets, and you don't necessarily have to win every point to win the match. In fact, there's a special name for matches where the winner actually won a lower percentage of points. They're called kind of like the lottery matches, because it's just it seems a little bit like they kind of
there was some luck involved.
Yeah, a bit of chance or luck on that. It's rare. It happens maybe 5% of the time, but still it points out the fact that the nature of points in tennis are a different thing than in a lot of other sports where there's an incentive to win every single point. So it kind of makes you think, well, maybe this would be one of the sports where this expectation, this theorem breaks down. But it turns out that if you focus on breakpoints, now these are situations where a receiver has an opportunity to win a game. And that's a special situation in tennis because there is a strong serve advantage. Just the nature of the serve usually gives the player that's serving an edge for winning those points. And so more often than not, players win their service games when they're serving. And anytime that doesn't happen, it's a real opportunity for the other player to take an advantage, a position of advantage. And in fact, most matches are won based off of breaks of serve. The only instance where that isn't the case is when a set has to go to a tie break. But by and large, matches are decided on the basis of the small subset of these break point opportunities. And if you focus on that, and that basically becomes your, let's say, breakpoint, breakpoints one becomes your points under this Pythagorean model, that you can find a strong relationship between that and a player's overall match win expectations over a period of time. And not only that, but it turns out the exponent is very similar to the one found in baseball, which kind of makes sense because if you look at the number of break points that are typically involved in a particular match, it's kind of a similar scale or range as runs in baseball.
Okay.
So, yeah.
Interesting. And the method for demonstrating this, is this, is it like coming up with a theory and then back testing it to a bunch of data, or how did you arrive at the notion of using the breakpoint?
Well, it's interesting. You can actually represent that Pythagorean relationship even with a general form with, let's say, the exponent being an unknown parameter. You can express that as a linear model. So it actually has a form. You can then investigate the simplest form where you're just looking at, let's say, one run type or point type. And then the goal is just trying to find what is the best exponent. That can all be done within a linear regression framework. So very kind of simple just to do a basic application of the model. The thing that's more of a question is what time periods are you looking at, and like what is the period over which you're forecasting? And that's really, you want to maybe consider how it might be used. So in tennis, you might expect that maybe after a few months into a season, there'd be an interest in projecting where that player is likely to be at the end of the season, and so on. Obviously, if you're a month out from your last few events of the season, doing that kind of projection might be less relevant. So we looked at sort of projecting 6 months out, 12 months out, and set up the training data for that purpose. But that's all almost like tuning parameters in terms of how you're going around to evaluate the approach. But that basic form fits within our kind of basic regression framework.
So what are some other ways that you've applied machine learning to this type of work?
Well, a few interesting things that we're working on now. One was actually started as a hackathon during this year's Australian Open, which was nice because it was sort of in parallel. We had, one of the majors underway, the first major of the year, and then we had this big data science competition. So
that's awesome.
Yeah. So that at the end, we ended up having thousands of data scientists participated. And the goal of the project was to use the tracking data we were talking about to classify the ending shot. So in tennis, there's a lot of interest about how a point ends in terms of was it a winner, unforced error, or forced error. So those are kind of the three mutually exclusive categories that any shot that ends a point can fall into. And you'd be amazed, but today that labeling, it's done at professional events, but it's still done by a human that's sitting on court and actually entering those labels with every point. And as you can imagine, it's labor intensive and probably not the best job, although if you're a tennis fan, I guess you wouldn't mind getting to sit down there. But one issue is actually consistency with those labels. So if you look at some of the unforced error winner stats from event to event, they can look quite different. And there was actually, I noticed at a recent Davis Cup event, sort of the tennis forums went a little bit crazy because there were clearly some problems in how those stats were being tallied. So you'd like to be able to, have a more efficient approach and also one that's more reliable from event to event. So we were thinking, well, we've got this tracking data here and it tells you about the nature of shots in such detail, like maybe you could build a classifier to automate that labeling process. And that was really the goal of the hackathon, was almost kind of a proof of concept of like, if you just had a lot of data science talent look at that problem over a few weeks period. How far could they take it? And the prize winning model actually was able to get 95% accuracy in the out of sample testing. So that was much more than we hoped, and quite promising, I think, for taking that even further with more data that we collect over time, and building something that we might actually start using in events. And I think not only for that particular use is it something that we're interested in, but I think it's a type of model that we could also use to maybe develop other metrics. Because if you think about it, being able to say how likely is a shot a winner versus an error, you can almost treat that as a measure of the shot's difficulty or quality. And you could apply that to any shot happening in a match. And so that could be a really interesting sort of extension or additional product that could come out of that kind of modeling work. So that was one that is kind of a recent development for the group.
Now that's really interesting. Can I interrupt you and ask, how does that 95% compare to what the humans that are sitting on the line recording that data tend to run?
Well, that's an interesting question because there's no gold standard. And that's one of the things that is an issue around, the consistency, because you only have one person at any particular time that's actually doing this in practice. So I don't think we really know if there is an error in some sense in how it's being classified. It's difficult to say because there's some subjectivity, particularly around the distinction between a forced and an unforced error. And in fact, for that reason, some tennis statisticians just don't really like the system at all because there is this element of subjectivity, because it's like, how far do you take it? Is it a shot that would be unreturnable for the average player, or do you try to make it specific to that player? So that means what is an unforced error for the 100th ranked player in the world isn't the same as for Roger Federer, for example. Right. So there's this kind of gray area in how these things are defined. So so we don't really know. I think the advantage would be that with having a system like this, you at least would know that the machine is always going to follow the same rules. And that's something that you can't be guaranteed of with using a human classification, particularly when it's only based on one person's opinion at any individual match.
Do you happen to recall any of the details around the winning model and its model type and general structure?
Yeah, so the winning model, the first thing, and this was true actually, what we did was we took the top 5 based on their out of sample testing performance, and we asked them all to provide some documentation about their approach. And there were some characteristics that were true across all of the top 5, and that included combining the men's and women's data in one model. And they all did extensive feature engineering. And so I'm sure the practitioners out there know like how important that can be to improving performance. And this whole experience really gave me an appreciation for that. And I would say probably that was the thing that separated the ultimate top prize winner from the others, was the extent of the feature engineering, some of which include basically just trying all kind of possibilities of combinations among the features that were provided, but also giving some thought to things that would potentially be relevant. So like there were some distances that were calculated from, player to player and things like this. So it was kind of a combination both of sort of, substantively driven feature development, and then others that were just more kind of just expanding the feature space. And other than that, I think a lot of the top models considered boosting types of approaches, and those seemed to work particularly well just on the basis of how much they were represented among that group of models.
And a lot of ensembles in that group of models, or no?
I think one of the 5 did did a more formal ensemble in the sense that they used multiple ML classifiers and then effectively took a sort of an average among them. So there was one, but that wasn't actually the top winning. The top winning was just a pure extreme boosting approach.
And do you recall were there any deep learning based submissions that tried to forego the feature engineering and just toss a ton of data to a neural network?
There were definitely neural networks. I don't think anything would meet like a definition of sort of a deep architecture, which may be reasonable in this setting because what we provided were sort of summary features about the last two shots of any individual point. It wasn't like we just gave them, coordinates in space. So the data was already fairly handcrafted, you could say. So it wasn't a situation like deep learning has generally been most successful when applied to image data. And that data, is much more complex than what we were providing based off these kind of summary measures from the tracking data.
And then on the machine learning front, you've been doing some work on emotion tracking.
Yes. So this is more of like our image application. So a lot of the things that we've been discussing have been focusing on these tracking data, but at the same time that's been a very great innovation in the sport. We also recognize that we have all of this match video just sitting around and we're not really doing anything with it from like a statistical point of view or from a data capture point of view. So we've been thinking about, well, what are things that we're not able to get from the tracking data that we would want to have to try to understand the sport better? And one of those things is player emotion and just mentality in general. So in tennis, there's a lot of conventional wisdom about the importance of a player's temperament and mentality during matches and how they perform. But we don't really have any quantifiable data around those concepts. So it's in some way, it's kind of the most elusive area in tennis performance is really understanding the link between performance and player emotion. So we've been working on an approach to try to capture information about the emotions expressed during matches using just a single camera video. And we actually have a paper describing our initial approach that appeared at the MIT Sloan conference this year. And essentially, we have like 7 different emotion types that we think are particularly relevant to a sports context. And this is one of the reasons why the problem's a bit challenging. There's been a lot of work with facial recognition and expression capture that's been going on, and you can even see applications of it in your social media devices. But in sport, you kind of want to tailor the emotions that you look at because there are some things that are of more interest in a sports context, like how concentrated a player seems to be. Do they seem frustrated or nervous? These kinds of things. So a lot of our work is actually just constructing this kind of labeled data set. So we've been treating it like a supervised learning problem. And so a large part of the time that we spend is to construct that database. But we have an initial version, and then we've started to actually apply it and understand what it might suggest about how players react to points and how their reactions might affect their future performance. And the next kind of frontier for that would be to actually try to start doing it in real time. But that involves a whole nother slew of problems. So you have to be able to, in real time, identify player faces from other faces that you might see captured in a video on broadcast, to be able to label the right player to that face, and then actually do any of the prediction on a real-time sort of time scale. So those are some of the challenges that we're looking at right now.
Oh, sounds like really interesting work. it sounds like you're in the early stages and starting to build out this data set. Have you gotten to the point where you've started building models on top of it and trying to relate that to player performance, or are you still way before that point?
Well, we have an initial set of approaches. So we looked at a range of different, fairly standard types of machine learning models. So we had tree-based approaches, support vector machines, neural nets. And from that, we were able to find what in our initial training set was sort of the best performing approach for each emotion type of interest. And then we applied that to a group of players that we kind of know what their baseline should be just based on sort of popular opinion. And that was the big four. So the big four are Roger Federer, Novak Djokovic, Andy Murray, Rafael Nadal, four of the most successful male tennis players in recent times. In fact, like from 2006 to the present, they've won 45 of 49 Grand Slams. Those are the biggest tennis events in the year. So they're players that are quite well known in the sport, and so they kind of each have a personality profile. And we applied the emotion capture to establish sort of baselines for each of them. And it was almost a way of checking the face validity of what we were doing, because it's like even if our model is able to get a good level of accuracy against the training set's labels for each of these emotions, how do we know that they actually represent anything meaningful? So that was why we wanted to kind of look at a group of players where we kind of have some idea of how they differ in terms of their typical temperament. And that actually held up quite well because, for example, it showed that the predominant emotion for Nadal was anxiety. And that was one that, was an expectation for him compared to the other three players. Whereas Roger Federer was the least expressive of the group. He was, if anything, he was more focused at any particular point in time than any of the other emotions. So that was a promising result. And then we started to look at, for that group, what the relationship was with performance. And we did find that there were strong associations with the number of the emotions that were captured and how that player was performing in the matches that we evaluated, which does suggest that there is some link there. But the interesting thing is that it was quite variable, like the nature of those associations from one player to the next. So it's still early days in coming to any very strong conclusions. But I think right now we can say that if there is a link, it's probably one that's player specific, the nature of how emotions influence a player's performance.
Yeah, I would think that if you've got four very winning players that all have different baseline temperaments, then it would be the difference between their baseline and what they're observed at in any particular point of time that would be kind of interest, as opposed to, the frustrated player never wins or something like that if there's a really good frustrated player.
Yeah, that's definitely one of the things that we're interested in evaluating more broadly as we collect more and more of this emotion data. Is it, just the absolute intensity of any particular emotion, or is it, how much it represents a change from what's normal for a particular player that actually matters. And if you just look at, the top of the game, and it's been true historically, like you go back to Borg McEnroe and you couldn't find like two more opposite personalities, but in terms of their success, they were quite comparable. And that's true as well today. You can have players that express a lot of anger and intensity, like an Andy Murray, against a sort of stoic champion like Federer. And so that in itself tells you that it's probably not that there's any like universal mentality that's like the one formula for being, one of the all-time best players in the sport, but it may have more to do with these kind of deviations from whatever a player's kind of norm is.
Right. Wow. Super, super interesting work. Thank you so much for taking the time out to share it with us.
Yeah, thank you for the opportunity, Sam. This is fun.
Is there anything else that you'd like to note for the audience, or anything that you'd like to point them to?
I guess just to say, I mean, for the maybe aspiring sports statisticians, I think there's definitely a lot of opportunity these days. I know our own group's been growing even over the past 6 months, and I think there's more and more appreciation for how data science expertise can help to advance sport in all areas. I didn't even mention, but I mean, there's more work being done on the business side, for example, and understanding, consumer behavior at sport and ticketing and things like that. So there's definitely more and more opportunity for statisticians, data scientists that are interested in careers in sport. And so I would definitely encourage you all to pursue it if that's a passion of yours.
Fantastic. Well, thanks so much, Stephanie.
Thank you.
All right, everyone, that's our show for today. For more information on Stephanie or any of the topics covered in this episode, head over to twimlai.com/talk/159. To follow along with the AI in Sports series, visit twimlai.com/AI in Sports. If you're a fan of the podcast, we'd like to encourage you to head to iTunes or wherever you catch your podcasts and leave us a 5-star rating and review. They are super, super helpful as we push to grow this show and community. As always, thanks so much for listening, and catch you next time.